Okay, so we're going to talk about polar equations and graphs. And, well, I was thinking about this. When I was a trig student, I thought I was getting to know all there was about math. I thought I knew everything. And that I was getting pretty close to like the edge of knowing all the math. And I was wrong, like real wrong. So something I think about, like, as I introduce this to you, is that, like, math is huge. And actually, we are still discovering new things about math to this day. It's kind of, like, amazing, actually, that there's still more things for us to discover, and they're all based in, like, logical thought. It's kind of crazy. So you can take a lot of math after trig. Okay. So anyways, I bring that up because it seems like that's a good segue to what if I told you there are other coordinate systems. So usually before trig, you've seen the rectangular coordinate system, but we are going to learn about the polar coordinate system. It's a new thing. And yes, actually, there are still other coordinate systems out there. You have not learned about all of them. There is not just rectangular and polar. There's actually more. So that's my plug to you to go out and find out what other math is out there. Okay, so for the polar coordinate system, so what do we need? We need what is known as a pole, which is a point in the rectangular land, and then we also need the polar axis, which in rectangular land was a ray. Okay, so it looks like this. This is like how we kind of plot things, I guess, in the polar system. Okay, so let me show you the polar system. Are you ready for this? Are you sitting down? Are you sure? Hatsa! Okay. It's not rectangular. It's a circle on a circle on a circle. So check it out. So on the outer parts of the circle, so you can kind of label this as much as you want, I guess. But a lot of times we'll use like the unit circle, or maybe we'll like subdivide up parts of the unit circle into smaller parts. But this is like the radian version of the polar coordinate system, and then this is the degree version. So you can do degrees or radians, of course. And okay, so polar and rectangular, they make totally different looking graphs, right? Because this is like a completely different axes. So when we convert from one to the other, we get very different looking graphs. So just to kind of, how do we convert, I guess, first of all? Because when you go from rectangular to polar, you're going to make like a new thing. So this is how we convert. And if you've been watching my videos on just converting to trigonometric units or trigonometric numbers, then you're already familiar with this. So it's the same stuff. And okay, so let's play around with this a little bit. So I've got an example here where we're going to plot each point, and then we're going to convert the point to rectangular. Okay, so the first point is this, 3 and 45 degrees. So I want to point something out here now using this. So in the rectangular coordinate system, we think of things as x, y. Now, when we're talking polar, we don't have x, y. We have r theta. And so this is how you make your r, this is how you make your theta. And you can use r theta to get you back into the rectangular coordinate system. So that's how all of this is going to relate to what we're talking about. Okay, so to actually like plot this point is pretty simple. So first, you want to figure out on these rings that you see here, on these circles, you want to find the third circle. Boom. Okay, there you go. And then you want to find where is 45 degrees. Hatsa. Okay, we're good. So then you look at, you can take from 3, move up to where we're at 45 degrees. This would be the point 3 and 45 degrees. And then the idea, so this would be graphing the point. And just to kind of extend this a little further, something that we understand about this is that this point, it just lies on this ray. That is just like what that means, okay? So this is the ray that's kind of extending out, and it starts from the center and then goes out. Okay, So now if I want to convert from polar to rectangular, I think this is pretty easy because you can just use this x and y, and then this is your r, this is your theta, so it's just plug and chug. So I can plug in the 3, I can plug in the 45 degrees, I can work this all out. So taking this point from polar into rectangular, here would be my rectangular coordinate. Okay, so let's do another one. Let's work with, how about radians? Okay, so I'll show you how this can get a little weird. So I've got -4 and pi over 3. So how do you get to -4 when we're in the circles? Okay, so what it means actually is that you're going to look at 4. So here's where we're at, the fourth circle. 1, 2, 3, 4. But the -4 means that you're going to, since this is a negative r, you're going to go in the opposite direction. So we're here at 4, but instead of going, so normally we go this way, but now we're going to go in the opposite direction. So that's what the negative means in that case. Now, here's where this can get a little funky. Pi over 3. So if I'm starting from here and I go up to pi over 3, so this is when this would be where pi over 3 is. So this is kind of awkward, right? Because it's like, well, we're coming up here to pi over 3, but I need to go this direction. So how do I reconcile that? Okay, so what this means actually is I have this ray coming out from here, but since my r is going in the opposite direction, it's going to lie on the back side of this ray. That's how you interpret that. So it's going to lie right here. And so we kind of just understand then that the point lies on this ray going just in the opposite direction. That's how you interpret that. Okay, so as far as the conversion to rectangular coordinates goes, I think this is pretty straightforward. So I would just say pause the video and try it just to make sure that you know how to do it, and then hit play when you're ready. So here we go. There's everything, and there's my rectangular coordinate system, rectangular coordinates. Beautiful. All right, so one more. So what about if I have a positive r and a negative angle? Okay. So positive r, so going to 3, so I go to that third circle, so 1, 2, so here's the third circle. And then just to interpret negative pi over 2, so we just, like, where would negative pi over 2 be here? It would be right here, right? So this is the equivalent of negative pi over 2. So the point, then I follow along 3 and I come over to here, boop, and then I just, again, I know, like, what this means. So this is me plotting the point, but also I just know that this lies on this ray. Whew. Okay, so last time we're converting, again, I think you should try this just to make sure you've got it. Hit play when you're ready. So I plug everything in as you see here, and so I just get the 0.0, -3. And actually, if you look, so when we look at that, that corresponds, like where it's lying on the unit circle, that actually does correspond to the rectangular coordinate system, right? This is 0, 3, and it's also 3 negative pi over 2. So there is that occasional overlap with this. So things do get kind of interesting since we're working with a circle, but there is some relationship. You know, there is that relationship back to the rectangular coordinate system. So you could kind of think of having these axes run through this way, and we'll talk about that a little bit more in a second. Okay, so all right, so let's continue on. So something that's interesting about polar coordinates is that a point on the plane, so if you're in the rectangular plane, there's only that one point. That's it. Something that's kind of trippy about polar coordinates is there's actually like an infinite amount of pairs of your polar coordinates. So there's a lot of ways that you can kind of play around with this. So 3 other points for 3 and -10. How would you go about doing this? Well, there's like 2 levers that you can really pull. You can add or subtract multiples of 180, and you can play around with what your R value is, so you can make it positive or negative. So just playing around with that, if I added 360, so that's a multiple of 180, right? If I added 360 this, I could have 3 and 250. I could also make my R negative. That would be fine. I could also add 180 to get 3 and 70 degrees. And there's just infinite possibilities of what you can do here. So that's something that's kind of weird, I guess, about polar coordinates. And that's why if you were wondering, like, why does this earlier example work? Why can I do this? So they're all lying kind of on this same ray. So it's all good. Okay. So now, why don't we have you try to convert these x, y. So these are rectangular coordinates. So these need to be converted to polar, and then we want two other pairs of the polar coordinates. So why don't you try to convert these? You've got kind of all the information to do that. Go ahead and convert, and then come up with just two other points and hit play when you're ready. Okay, so I need to find my r and my theta. So, it's very familiar formulas to us. So I have my r is equal to 1 and my theta is equal to 30. So the conversion of this to polar would be 1 and 30 degrees, and two others that I came up with, -1 and 30 degrees and 1 and 210 degrees. But there's a lot of other ways you could have come up with this, right? So add 180, add 360, 1, -1, whatever you want. Okay, now, polar equations, you know that you have a polar equation because it will be in terms of r and theta. So you know that you have left the rectangular coordinate system and you have gone to the crazy circular polar coordinate system when you see the r's and the thetas. And okay, so what I want to do is I just want to do like a couple of really basic graphs just to kind of show you some fun things with this. So let's say that I've got the equation y equals x minus 1. So we know that this is a line, right? We know this. So first of all, how could I convert this into a polar equation? Okay, what I like to do is I like to have my x's and y's on the same side if they're not, and then I just make this substitution, right? This is what x and y equal. X is r cosine theta and y is r sine theta. So if I make that substitution, I can rewrite my equation as so, and then I can factor out the r. Now, your life is usually easier if you isolate r when you are trying to graph. So it's generally a good practice. A lot of times you'll see that r is isolated in some way. So as far as like how would this actually look, we know it's a line, right? And this is actually something, this is like, you wouldn't normally graph this in the polar coordinate system, but what would happen if you were trying to graph a line? So remember how I told you, like, we still have that kind of x and y axis connection. So the way that this would look, I'm not going to go too much into the points, but just like effectively what happens is, so this line will go through 1 here and -1 here. So it still just is a line even in the polar coordinate system. So this is not a very exciting graph. This is more just to show you how to convert to a polar equation. Okay, so let's talk about another one. So I want to convert this to a polar equation. Why don't you try to do this one on your own, and don't worry about the graph, just try to convert it and then hit play when you think you've got it. Okay, so first of all, I just want to note this is a circle. And so if I make the replacements with x and y, so I notice right away that I can factor out the r squared, and then I'm left with cosine squared plus sine squared. This equals 1, so this all boils down to r squared equals 25. And so I can rewrite that as r equals 5 or r equals -5. So remember, it doesn't matter if your r is positive or negative. So when I go to graph this, I know that r equals 5 coincides with r equals -5. Doesn't matter. Okay, so I just then, on this graph, I want to be able to show everywhere where r equals 5. So as I look around the rings, here's where r equals 5. So right here, and so here's how this graph would look. It's still just a circle, so I just trace all the way around this, and that would make my circle. Okay, now what if you want to graph other polar things? Okay, so let's graph r equals 1 minus sine theta. So before I get into this, I just want to remind you, what does this graph actually look like? Okay, so I've gone to desmos.com and I've just plugged in 1 minus sine x. So this is what the graph of 1 minus sine x would look like. So nothing too crazy. We remember all of this. So we've moved the sine graph up 1, and then actually we've also flipped it because we've got this negative in front. So okay, so this is what 1 minus sine x looks like in the rectangular coordinate system. And just like always, when we don't know how to graph something, usually what we do is we make a table. So we're going to make a table, but we're going to make it in the spirit of now our polar coordinate system. So instead of having x and y, I'm going to choose a theta. and I'm going to plug it into 1 minus sine theta to get an r. So I have just chosen a bunch of degree measures that go around the unit circle, and you really do want to go around the unit circle, right? So if you think about how that graph paper looks, it's going from 0 to 360. So you do want to hit a bunch of degrees as you go around. So that's kind of why I go into so much depth. And so as you can see, this can kind of be a lot of work. And I went ahead and I just like found the points. And okay, so how would I actually graph this then? Well, we've already talked about, so these points here, these are now my r's, right? So I've got my theta, and now I've got what the value of my r will be. So if I wanted to graph something like 0, 1, so if I come to this here, here's 0 degrees, and then here's 1. Okay, what about 30 degrees and 0.5? All right, so if I go onto my graph, so here's 30 degrees and then 0.5. So this graph's is a little small, but I think we'll be able to make the point. So okay, here we go. There's that point. And then what about these 3 points? So I got 45.29, 60 degrees, 0.13, and 90 degrees 0. So you see that these points are getting progressively smaller in terms of the value of r. So if I were to graph that, I'm going here, here, doot, 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 doot. So I'm kind of coming down. Okay, and okay, so I think you see just like how you'd go about this. So it's graphing just like, just like you really would in the rectangular coordinate system. So let me just plot the rest of these. So it's kind of a mess, and it's a little hard because this graph's a little smaller. So I will just trace the outline for you. Oh, it's a heart. That is so much better than a bunch of waves, right, guys? This is like such a cuter graph. So this is something that happens with polar. So when you get into polar coordinates, you actually get these really cool shapes like this. And, I love that. I love that about polar. So when you play around with it, that's effectively what happens. And just to show you a couple of other fun things that happen in polar coordinates. So I have here, so r equals 4 cosine 3 theta. So just like look at the unique shape that we get. It's in red. So it creates like much more interesting graphs than what we get in the rectangular coordinate system. A lot of people can get a little arty with these. Let me show you maybe just a couple more. Okay, so here I've plugged in r equals cosine of 2 theta, so this makes a cool like infinity symbol. And then finally I plugged in r equals negative theta, and this makes a cool looking spiral. So this is kind of like a thing with polar coordinates. And so that brings us to the end of this introduction of just polar coordinates. And actually, if you're one of my trig students, this brings us to the end of trig. So I hope this has been a great class for you. If you have enjoyed it, and if you've enjoyed the videos, please consider giving them a thumbs up or a comment. Really appreciate it when you guys do that. And so before I let you go, so now you finally get this classic trig pseudo joke. IR 1 minus sine theta math. What does that actually say? All right, guys. Well, hopefully I'll see you around.